In this chapter, we are going to talk about solutions, the properties of solutions, calculations that we can do with solutions, and concentration. In this particular screencast, we're really going to focus on some of the properties of solutions. And so I want to remind you that a solution is just a homogeneous mixture of two or more substances. Right? And the terminology here is basically we have one substance that's dissolved in another substance, and then that solution forms. And so we describe those two components as a solute and a solvent. A solvent, right, is the component that is present in the larger amount, and the solute is any component in the solution other than the solvent, right? So you can have one or more solutes, right? Now, solutions can be any sort of mixture of the phases, right? You can have two metals that are mixed together. So you could have two solids, basically. You can have two liquids. You can have a gas mixture, right? When we talk about these mixtures, you can also have a gas and a liquid, which we're going to talk about in the next screencast. One of the solutions that we are going to run into most often is an aqueous solution, right? And in this, water is the solvent, right? And a lot of times this is represented with an AQ, and we've already talked about this just a little bit. If you look at the image here, this is an example of a solution. We have water here, table sugar is sprinkled into it, and now we have a homogeneous solution. Let's look at, some of the properties of solutions, okay? So I want you to know that this is a clear solution, and what clear means is it's not cloudy, and then it's also a colorless solution, right? It does not contain any color. So when we talk about solutions, it's important to understand that solutions, and I'm going to abbreviate solutions like this, are clear and transparent, and they can be color or colorless. I don't know if you could hear that, but my puppy dog just snored, so that's why I was giggling there. These basically are a homogeneous mixture. With uniform properties throughout. Particles will not settle. Over time. It's important to understand that the volumes of solutes and solvents are not additive. And so what I mean by that is if you take 1 liter of ethanol and you add 1 liter of water, it does not equal 2 liters. It will be smaller. It'll be a smaller volume. And the reason for this is basically when two or more molecules are mixed, the interactions are just complex. And so what can happen here is you have solute, right, particles, and you have solvent particles. And when we talk about the interactions here, we're not talking about chemical reactions, right? When we talk about a solution, the components do not chemically react with each other, but they do interact with each other through some of those intermolecular forces that we talked about previously. And so some things to keep in mind is the solvent molecules can interact with other solvent molecules. Okay. The solvent molecules can interact with solute molecules. And then if you've got more than one solute, the solute molecules can interact with solute molecules. And so the volume is determined by the size of the individual molecules and how they fit together. And so sometimes that's why the volumes aren't additive. Sometimes it can be smaller or larger. Now, it's important to also understand when we're talking about solutions, two other kind of categories that we'll see. These two other categories are colloids and suspensions. Now, when we talk about a colloid, okay, we have solute particles distributed through a solvent, right? But it's not homogeneous. Right? And so what do we mean by that? That means eventually what we'll see here is that we have particle sizes that stay suspended in solution. And to us, these really look cloudy, okay? So the particle size here, right, is 1 nanometer to 200 nanometers. Now, let me tell you this. Your book says 1 nanometer to 200 nanometers, but other books will take that up to 1,000 nanometers. So I'm trying to stay with your book and your homework system, but I just want you to be aware that definition is a little bit fluid, but this is the one that we're going to stick with right now. And these basically stay suspended in solution, right? And those, and it looks cloudy to us. And a really good example is milk or cream, and homogeneous milk or cream, right? And so these have large like protein and fat particles that float around, but they don't settle out over time. So that's called a colloid. You can also have a suspension. Right? And this is a heterogeneous mixture that has particles larger than 200 nanometers that over time will settle. So an example is muddy water. If you get muddy water over time, the dirt particles will settle out. Another example is blood, right? The blood cells are really large. They will settle out from the plasma. And so here is an example of that, right? Now this has been centrifuged to help this along, but that's so you can see the blood here and then the plasma here. Now, I want to talk about something else before we get in here. And so I want to just add a page to this. And I want us to define solubility. Right? When we talk about solubility, this is how much solute can dissolve in a solvent, right? So how much solute can dissolve in a solvent? And we have some general solubility trends. Now, solubility is generally given to us in some sort of amount per volume. So for example, it could be 100 grams per liter, right? And then over that, so if you have something that's over this, you would end up where you have a solution where things would not dissolve, right? But under it, it will. Now, there are some trends for solubility that we can use to help us predict if something's going to be soluble. And so when we talk about these trends, all right, the first one is that likes tend to dissolve likes. And what do I mean by that? Well, polar molecules between the polar, right, and nonpolar molecules, right? So if there's less difference, they're more soluble, and if there's a greater difference, they're less soluble. So we are going to look at some examples of this in the next screencast. The second thing is temperature, right? And what we're going to see is that as temperature increases, the solubility increases for most solids, right? But solids and liquids. But if you increase the temperature, then you decrease the solubility for gases in liquids. And we're going to look at that with Henry's law in the next screencast. And then the third thing is pressure. Now, pressure doesn't affect solutions that are like liquids or the solutions of solids. However, this does matter when there's gas in a liquid, and we're going to talk about that as well. So I wanted to talk to you about solubility as well as some of the different trends. Now let's talk about saturated and supersaturated solutions. What you're going to see here is that I could not go back. It would mess up your screencast. So I just brought the image from the previous slide to this slide so that we can talk about it and give you those definitions. So when we talk about solutions, we can have a saturated solution, and this is already written on your slide with the molecules, right? And this is one that contains the maximum concentration of a solute in a solvent at a given temperature. Then you can have a supersaturated solution, where this is a solution containing more than the maximum quantity of solute, right? Predicted to be soluble at a given volume and temperature. Now, this is an unusual and unstable situation, that supersaturated solution, and it can occur if the temperature of the solution is raised, allowing excess solvent to dissolve, and then as the solution cools down to the original temperature, the excess solution does not precipitate but stays dissolved until you either scratch the side of the flask or it gets disturbed in some way, or you add a crystal to it. Hand warmers are a really good example of this. If you have seen reusable hand warmers, they contain a supersaturated solution, and what you'll do is you'll pop a little piece of metal in them, and that's enough to cause it to crystallize. And when it crystallizes, it produces heat, and so these are reusable hand warmers. So I want to talk to you a little bit about kind of some of the things that I've got for you here. One of these is, when we look here, this is an example of seawater versus saturated NaCl. When we talk about seawater, it's got 3.3 grams per 100 milliliters of water. And then when we have, and that's its concentration. And when we have a saturated solution, this is saturated NaCl, it contains the maximum concentration of a solute at a given temperature, and that's 35.9 grams of NaCl per 100 milliliters. And so I wanted you to see how those numbers were written. And then this is an example of a supersaturated solution, where this is supersaturated, it's been heated and cooled down. A seed crystal is dropped in, and it causes the solute to precipitate out and go back to it just being a saturated solution. So those are different examples that I wanted to show you before we went on to our next topic. Now, when you have an excess of solute beyond that solubility limit and it's added to a solvent, right, it dissolves and establishes an equilibrium. And so when an excess of solute, right, beyond the solubility limit is added to a solvent, it dissolves and establishes a dynamic equilibrium between the dissolved and undissolved solid. So what we're talking about here is if you have a solution, right? And so this is unsaturated, it's below that solubility limit, and you add more solute, and now it is above the solubility limit, so it's saturated, and there are some crystals here and no more can go into solution, what's happening is the dissolving of the particles and the recrystallization of the particles is happening at the same rate or the same speed. And that's what we talk about when we talk about equilibrium, right, of our saturated solution. Now, how does this apply to us? I love a good application, and a really great application here is gout and kidney stones. So the conditions of gout and kidney stones occur when compounds build up in the body and exceed their solubility limits. So gout and kidney stones occur when compounds build up in the body and exceed their solubility limits. And so for gout, that compound is uric acid. Now I've got the structure of it there. I'm sorry, I said uric acid. It's uric acid, right? And basically, there's an excess of this, and crystals form in the cartilage and tendons, and it can be very painful. So there's an example of gout, and there's an example of the crystals. Now with kidney stones, this can be the uric acid again. But also, it can be calcium phosphate, which is an ionic complex, right? And or calcium oxalate, right? So these conditions are caused by crystallization when these compounds exceed their solubility limits. So this completes our screencast. If you have any questions, please feel free to pop by my office. In the next screencast, we are going to look at Henry's Law.